Have you ever wondered how things grow so fast, or why we use logarithms to simplify them? Today, we'll break down exponential and logarithmic functions and see how they're actually opposites of each other. Let's start with a fundamental idea in math: exponential functions. An exponential function is a function where the variable is in the exponent or the power. Instead of adding repeatedly, exponential growth is about multiplying repeatedly. For example, if we take base 2, 4, 8, 16, you can see the numbers grow faster and faster. So the key idea here is backhand index pointing right. Exponential means accelerating growth driven by multiplication. Now, let's compare exponential growth with something more familiar: linear growth. Linear growth means we add the same amount each step. Exponential growth means we multiply each step. At the beginning, they might look similar, but very quickly, exponential growth becomes much larger. Backhand index pointing right, that's why exponential patterns can feel surprising or even overwhelming. But exponential functions don't always grow. They can also decay. If the base is greater than 1, we get growth. If the base is between 0 and 1, we get decay. Growth means values increase rapidly. Decay means values decrease and approach 0. So, the same structure can describe both population growth or drug concentration decay. Now, let's look deeper. The behavior depends on the base A. If A greater than 1, we get growth. If 0, A less than 1, we get decay. If A equals 1, the function is constant. If A less than or equal to 0, things become invalid or unstable. So the base completely controls the shape of the curve. Backhand index pointing right, you can think of the base as the growth engine. Now we introduce the logarithm. A logarithm is the inverse of an exponential. It answers a very specific question. Backhand index pointing right, what power do I raise a base to get a certain number? So instead of computing the result, we're solving for the exponent itself. Now here's the key insight. Logarithmic and exponential functions are mirror images of each other across the line y equals x. They literally undo each other. For example, e squared is approximately equal to 7.39. The natural logarithm of 7.39 equals 2. So one builds the value, and the other retrieves the exponent. Backhand index pointing right, this is why they are called inverse functions, because they help us simplify large-scale data. Without logs, 1, 10, 100, 1000, very hard to compare. With logs, 0, 1, 2, 3, everything becomes linear and easier to see. Backhand index pointing right, logs transform exponential patterns, linear patterns. Huge differences, manageable comparisons. That's why logs are widely used in biology, data science, machine learning. There are a few common types of logarithms. Base 10, common log. Base E, natural log. Base 2, used in computer science. Each one is useful depending on the context. Finally, just like exponentials, the base controls behavior in logarithms. If A greater than 1, the log increases. If 0, A less than 1, the log decreases. If A equals 1 or A less than or equal to 0, not defined. And very importantly, backhand index pointing right, logarithms only work when the input x greater than 0. So, to summarize, backhand index pointing right, exponential builds growth, backhand index pointing right, logarithm explains that growth. And together, they form one of the most powerful relationships in mathematics.